What is the main problem addressed in the paper regarding language models training efficiency?
The main problem addressed in the paper regarding language models training efficiency is the issue of unnecessary document truncation during pre-training. The paper highlights that the widely used method of concatenating all documents together and then splitting them into sequences for training leads to data integrity loss and potential hallucination in models. This truncation reduces the amount of context available for each segment, impacting next token prediction and model performance. The paper proposes a solution called best fit packing, which efficiently groups training data without unnecessary truncation, maintaining training efficiency while preserving data integrity. Best fit packing eliminates unnecessary document truncations, leading to superior model performance and reduced hallucination in downstream tasks.
How does best fit packing method propose to address the truncation issue in language model pre-training? Provide a step-by-step explanation.
The best fit packing method addresses the truncation issue in language model pre-training by first segmenting every document into chunks that are at most the model's maximum sequence length. Then, the method selects a number of these document chunks to fill up as much of the sequence length as possible without breaking any of them. This step is crucial to ensure that the training sequences are as token efficient as possible. The selection strategy, referred to as the packing algorithm, is designed to be scalable and fast enough to handle datasets of billions of documents efficiently. The algorithm is formulated as a combinatorial optimization problem, where the goal is to find a partition of the smallest possible size to generate the fewest number of training sequences. The best fit packing method employs an efficient algorithm that scales linearly with data size and achieves the same level of compactness as the traditional concatenation method, thereby incurring a negligible loss in training efficiency. By completely eliminating unnecessary truncation for document lengths below the model's context length, best fit packing effectively preserves the integrity of the majority of documents and limits truncation only to longer documents where it is absolutely necessary.
What are the theoretical benefits of using best fit packing method over the traditional concatenation approach in language model training?
The theoretical benefits of using the best fit packing method over the traditional concatenation approach in language model training include the elimination of unnecessary document truncations, preservation of data integrity by grouping training data efficiently without sacrificing training efficiency, and reduction in hallucination during model training. Best fit packing ensures that documents are segmented only when they exceed the model's context length, thereby preserving the entirety of individual samples and reducing the loss of information caused by fragmentation. This method effectively addresses the issue of data integrity by minimizing unnecessary truncation, which can lead to ungrounded next token prediction and increased model hallucination. Additionally, best fit packing optimizes the grouping of training data into sequences, maintaining training efficiency comparable to concatenation while significantly reducing the amount of padding tokens used. The method also enhances context awareness in models, leading to improved performance in various downstream tasks such as reading comprehension, natural language inference, context following, summarization, world knowledge, and program synthesis.
How are the empirical results presented in the paper to validate the effectiveness of best fit packing method?
The empirical results presented in the paper to validate the effectiveness of the best fit packing method involve pre-training a set of models with inputs formatted by both concatenation and best fit packing, ranging from 7B to 13B in model size and 2K to 8K in sequence length on both natural language (NL) and programming language (place) data. These models are then evaluated on 22 tasks covering reading comprehension, natural language inference, context following, summarization, world knowledge, and program synthesis. The experiment results demonstrate that models trained with fewer truncations using best fit packing show superior performance and exhibit less hallucination compared to models trained with the concatenation method. The paper quantifies the benefits of truncation reduction in various downstream scenarios empirically, showcasing the positive impact of the best fit packing method on model performance across different tasks. The results consistently show that the best fit packing method either outperforms or matches the baseline in all evaluated tasks, with no statistically significant degradation observed, thus validating the effectiveness of the proposed approach in improving model performance and reducing hallucination.
What is the impact of truncation reduction on downstream tasks in the experiments conducted in the paper?
The impact of truncation reduction on downstream tasks in the experiments conducted in the paper shows that models trained with fewer truncations demonstrate superior performance and exhibit less hallucination. Specifically, the best fit packing method, which eliminates unnecessary document truncations, leads to improved performance in various tasks. The experiments reveal that best fit packing improves reading comprehension by up to +4.7%, natural language inference by up to +9.3%, context following by up to +1.6%, and program synthesis by up to +15.0%. Additionally, best fit packing effectively reduces closed domain hallucination in the models. The results consistently show that the models trained with best fit packing either outperform or match the baseline in all evaluated tasks, with no statistically significant degradation observed. This demonstrates that reducing truncation through best fit packing enhances the model's performance and reduces the risk of hallucination in downstream tasks across different domains and context lengths.
What future research directions are suggested by the authors in response to the limitations of the proposed method?
The authors suggest future research directions to address the limitations of the proposed method, such as investigating the impact of best fit packing on different model architectures beyond transformer-based models, exploring the application of best fit packing in scenarios where document boundaries are not clearly defined, and studying the effectiveness of best fit packing in reducing hallucination in other types of language tasks beyond the ones evaluated in the current study. Additionally, the authors propose exploring the combination of best fit packing with other data grouping strategies to further enhance data integrity and model performance, as well as conducting research on adapting best fit packing for multilingual models and exploring its effectiveness in low-resource language settings. Furthermore, the authors suggest investigating the scalability of best fit packing to even larger datasets and exploring its potential application in other domains beyond natural language processing, such as image captioning or speech recognition tasks.